Okay. And now I admit everyone. And I remove the waiting list so that the others can join without any further ado. Okay. Good morning. Good.
Okay, finally I'm here.
Yeah. Hi, Lorenzo.
Hello, everyone.
So we do have both the speakers, Steve and Lorenzo, so we can start this webinar. So thanks for joining. I removed the waiting list, so those who wants to join later can do that without any action from my side. As you know, we typically record these webinars in order to share this material just with the with the members of CTSoc. So I hope it's okay for you. As usual, I would like to start this webinar with just a few words about the technical talks, the idea of the technical talks. So I, first of all, thanks all those who joined it today. This is the 8th talk of this webinar series named the Technical Talks of CTSocs, which has been launched to create connections between the various technical committees that constitute the areas of the technical activities in CTSoc. So as you might know, but I hope that there is also people not yet member of the technical committees. We have 15 technical committees covering the field of interest of consumer technology society, CTSoc, and every month or 2 months, we have a webinar organized by the technical committees with the speakers selected by the technical committees. Today, we have a representative from the MDT, Smartphone and Mobile Device Technologies, and the Consumer System for Healthcare and Well-being. The technical committees are part of the technical activities areas. And within technical activities area, there is a board that is governing and supervising the activities of these technical committees. Each technical committee has a chair, a vice chair, and the secretary. So there are 45 people. Plus, there are other members in the technical activities board, the VP technical activities, myself, the CTSoc president, Wenchun Kao, the VP Conferences, Nabof Nabiki, the VP Publications, Fabrice Labo, and the VP Industry and Standard Activities, Rahed Abdullah. Within the technical activities area, there is also the Future Directions Committee, and together these entities and committees are responsible for sharing the activities that are performed within CTSoc and also provide opportunities for the members. Each technical committee has its own website, so you can check it. And the officers, chairs, vice chairs, and secretaries are helping a lot. And this is the case, for instance, of the MDT technical committee, so Masato, who is attending today, and the other officers, and the CSH, Alessandro, who is attending today, and the other officer who helped organizing this talk. As you know, new members can join our technical committees. We do have a membership application form. So in case you are not a member yet, you can use this form. And remember that you don't need to be an IEEE or CTSoc member to join. The family of the technical committee members is growing. We have now reached almost 1,000 members. And consider that these are not all IEEE and CTSoc members. So we are extending the family of CTSoc. And we are in charge of supporting a number of activities of CTSoc regarding conferences, publication, standards, education, and industry. And we are helping in many ways. So, for instance, regarding conferences, the technical committees help approving the call for paper of conferences, providing reviewers, contributing papers, collecting nomination for TC members, and for technical positions like chairs, workshop chairs, tutorial chairs, etc. Here we have a short list of ways in which the technical committees have created opportunities for members, but there's a page on the technical activities website describing what has been done over the last years. One example is the GEM conference, which has been organized last year in Barbados with the proposal, based on the proposal of technical committees. And this year will be organized in Turin. So it will be also at Politecnico di Torino, where I am now. So of course, here you are welcome to contribute and to attend, but also consider that there has been a great contribution of our technical committee. So thanks if you have been involved. I've been requested by the VP conferences to share also the current calls for paper open for other conferences, CTSoc conferences, like the Symposium on Consumer Technology in Bali this August, the ICC Asia in Vietnam in November, and ICC Las Vegas in January 2025. Activities of technical committees are related also to publications. So, for instance, the members of the technical committees have been involved in the definition of the editorial board of Consumer Electronic Magazine. There is also regulation for which, in order to propose a special issue in Consumer Electronic Magazine, you might need to be a member or be supported by officers of the technical committees, but there are also news regarding transaction in consumer electronics, which are publishing also the outputs of CTSoc conferences, which is selecting associated editors also based on the activity in the technical committees, and will be soon launching a new initiative called letters. There are other initiatives that I could mention today, like the IEEE Digital Reality Technical Community. This is not a technical committee, it's something different, which is involving not only Consumer Technology Society, which is the lead, but also other society like reliability, electronic packaging, engineering and medicine and biology, council and radio frequency identification, standard association, and robotics and automation society so far. So there will be opportunities within this technical community too. Of course, as the name says, it will be about digital realities and realities. So aspects related to digital twins, to extended reality, to the metaverse. So in case you're interested, please let me know. Now, coming to the technical talks, this is the last slide. I just want to recall you that thanks to the support of the officers, we are organizing these periodic talks. And well, the agenda for today is this one. And then I will leave the floor to Alessandro and Masato. We'll have two speakers today. Dr. Monk Wai-Hin Steve Monk from the TC on MDT, and Dr. Bacchi Lorenzo Bacchi from the CSH TC. So I will leave the floor to Alessandro and Masato for introducing the speaker. I thanks them. I thank the speakers a lot, of course, for their availability, and you all for attending. And of course, I'm looking forward to seeing you in the next webinar of our technical talk series. Thank you. Alessandro, Masato, the floor is yours.
Thank you, Fabrizio, and welcome everyone to this initiative. So I greet you all and thank you for participation. So the initiative time slot is, as usual, 1 hour overall, divided into two parts for the two speeches of today. So roughly there is 20 minutes each for the talk, including the part dedicated to Q&As. So in order to be all compliant with this time slot, I will try to moderate accordingly. And all the questions and answers should be asked and answered just after the presentation related. So once we have the presentation by Dr. Steven Mung, we can ask him for questions, and then the same with Dr. Lorenzo Bacchi. So I thank you all, and I leave the floor for a greeting to Professor Masato Oguchi from the MDT Technical Committee.
So maybe my turn first. So I'm Steve. Nice to meet you all. So let me share my presentation today. So can you see my presentation?
Yes, Steve, you can go full screen when you want. Thank you.
Yeah, full screen now. So nice to meet all of you. So today my title is The Challenge on Wireless Front-End Circuits in Mobile and IoT Systems. I'm from Research and Development Office from the Education University of Hong Kong, and I'm from MDT. So I think all of you have the smartphones, and the smartphones from 3G to 4G and behind in the past 10 years, it going very fast. And then I don't know whether all of you is a young or not, so you know whether iPhone 4 has the antenna issue in 2010, and then Steve Jobs solved that issue, and then finally a free iPhone case come out. So that's why there is many iPhone case now. So and then in 2021, so the number of smartphone users in the world may be more than 6.3 billion. So and then in the coming future, so maybe from 5G to 6G, Wi-Fi 7, millimeter wave band, and then satellite. So and then those standard, for example, 5G, NTN from 3GPP. So this kind of things related to mobile phone and IoT device. So then that's why I present this topic. So for the mobile phone, there is frequency and time division 2% FDD. So I select the 5G FR1, the frequency band sub 5G new radio. So and then there is also NB-IoT frequency band. So you can see that they share the frequency band, but the case is you can see that for IoT the bandwidth would be more narrow than the 5G. So because for IoT stuff, we don't need to have too much data rate. So then go back to the circuit. So because we are talking about wireless, so while there is wireless front-end circuit in mobile and IoT system, so what is front-end circuit is RF firmware we call RFFE. So there is a organization called MIPI, so they control the standards for controlling the chipset and those circuits in the wireless front end. And then the left side is 3G and 4G front-end circuit. Right side is the 5G and 4G circuits. So you can see that for 3G stuff here, so we have many bands in the mobile phone 3G standards. So for example, here band 5, band 1, band 40, and GSM. So at that time in the old circuit, we have individual parts for each band, and now we combine all of it in one chipset. So I will show to you in the later slide. So you can see that the circuit is now become more compact, and then everything become a one chip. So that's why it's more important we control the wireless front end. So and then in the RFFE circuit, the critical application is DC power consumption, and then the power distribution in terms of heat for the user level. For example, if you use your mobile, you can sometimes it's very hot because of the front-end circuit. So that's why the DC power consumption is important also, because the battery life is very important on portable device and also the reliability, because if there is something wrong on the reliability, your device is totally down. So, and then the RFFE circuit is one of the highest cost in the products, especially the power amplifiers. So I will talk about why power amplifier is very important in the front end, because it dominates the mobile RFFE system characteristic to meet the 3GPP standard. So in order to meet the 3GPP standard, we need the linearity, and also because we conserve the power consumption, that's why the current is also important apart from, and also the gain, but the most important two items is the linearity and the current. So let me talk about the simple concept for local for the power amplifier, because power amplifier is the things we transmit the signal or the data to the base station or to others. So because power amplifier consume the current, and then this is the active device, so this is very important in the front end circuit. So for the local is the technique we use for design the power amplifier. So that's why local is a technique to characterize the RF transistor to become power amplifier when operate in non-linear region. We also call that region is large signal region, because we need to amplify and deliver a large signal to the base station or to other places. So for the ideal transistor, the current strength over its maximum linear region. So here, so and then the MRT would be this one, and then the voltage also swing in the maximum range from 0 to 2 VDC. The DC is the MRT. So then we can calculate the low line resistance we call up with our optimum. So the equation is here. So the transistor is here, so we need to do the matching so that we can optimize to give the maximum efficiency. And then this one is based on the device level to design the power amplifier. But now I'm not talking about design the amplifier. This is the example for the amplifier, how to design the amplifier. For the design the amplifier, we are looking at the impedance here, the ZL. This ZL we need to use this equation to do the matching. So after everything done from the chipset designer, there is a power amplifier module come out. So and then this power amplifier module can be buy from the market, then we put in the mobile phone and then connect to other front end device to become a front end circuit. So and then this is called power amplifier module. So actually once we do the design in the mobile phone, we also need to do extra matching to tune the set out here to serve the application, for example, IoT device as well as the mobile phone. So this is some example for PAM, power amplifier module. So everything fully matched. So we just terminate 50 amp and then we can get the parameters and the spec and the numbers from the data sheet. So PAM is already optimized, and the trade-off between the power, efficiency, and linearity with different techniques such as local in the design level. So we already have that technique, and then we just buy it and then connect it together with other front-end circuit. So app input and output is already matched to 50 amp. So this is some example for PAM. So you can see that there's many device inside the PAM, many circuit inside, and then we just use this one connect to our front end circuit. So then we talk about the linearity, ACL and EVM, because we need to meet the 3GPP standard. For example, there is a signal here. So this is maybe 10 megahertz signal with QPSK. So we go to the PAM here, for example, 30 dBm. So of course the signal will be amplified, but the case is there is something wrong here. We call this is ACL. So this is other channel. So that's why we need to control this signal, and then we call this is ACL. And then also the EVM is also important because this is in-band signal. So if the EVM number is large, that means your signal will have something wrong in your mobile phone. So we can't transmit, and also some error. So this is some concept for linearity. So the case is the ACL is very important for the mobile phone because it will affect other channel. So some relationship between current, gain, and linearity. So maybe I talk current and linearity because for the amplifier, when we provide the input, there should have a gain in the amplifier, then there is output. So we will have a AM curve, output power, the gain, because the power amplifier gain is fixed, but the case is because there is some non-linear for the amplifier, when the output is larger, the gain will drop, and also the phase also drop when the signal of the output is larger and larger. So then these two terms will cause the linearity issue. That's why this is the indicator for linearity. So you can see that from this curve, the blue curve is the linearity. So when the linearity higher and higher, so they will be out of the 3GPP standard. For example, we have the acceptable level at here, but you can see that the red color is the efficiency curve. So you can see that when the power is higher, the efficiency will be better. That means your current consumption will be better. So that's why we want to have a power at here. But the problem is when we have the power here, we will have a back ACL. So that's why we will have a new term, for example, back maximum PAE here, and then maximum power here. So for maximum power for the data sheet, normally in the data sheet, we call maximum power is 27 in this case. So in this case, maximum means we can achieve the best linearity ACL. So that's why when you get the data sheet from the PAM, you can see that we have a maximum power. That means they will provide the acceptable ACL, but the case is the current is not good enough because the PAE is not good here. So that's why maximum PAE reach to saturate power here. So will become back AM, and back AM, PM here. So that's why you can see from blue to red here. So we need back off power back off here so that we can achieve the good linearity. That's why we can't operate the power amplifier at this point because we need to get a good linearity. That's why we need to get the power back off. In this case, it will have 4 dB power back off because this power back off depends on the signal we use. If the signal, for example, for 6G, the modulation would be more tough, and then the back off would be more, maybe go to here. So that's why there is challenge between current and linearity in the power amplifier. So let's go to example here. So the blue one is already the PAM. So, and then once we connect the things together for the front-end circuit, we will have the power amplifier, switch, duplexer, and also switch at the end, and also the antenna here. So at 3GPP standard, we came is 23 dBm, and then if your PCB design and your component select for the front end is bad, so there will be higher loss here. In this case, for example, the loss in this path is 3 dB. So that means we need 23 plus 3 dB, so that we need the power amplifier delivered at this point is 26 dB. So then we need the data sheet is CAM 27, but now we want 26 is already enough because we only deliver 23 dB. So then maybe here now I go to another figures. So this is more simplified. So this is the palm. We deliver 26 here, and then data sheet CAM is 27. So finally we have 3 dB loss here, finally 23 here. So then that means we can deliver 26 dBm. So in the curve here, so I select it out, power at 27 dBm, ACR is minus 40. At 26 dBm, ACR is 42. So you can see that higher power has higher efficiency and PAE 35, 30. So that means you can see that there is a room in linearity 42 at 26 dBm compared to 27. So because the acceptable level in this case is 40, so we can have 2 dB room. So that's why we can do extra additional matching. We also call this is low pool. So in this curve, in this figure is called Smith chart. So different points on the Smith chart here on this figure is the impedance load on the ZL, the amplifier here, this point. So this number is at the center, 50 ohm. So that, and then we extract the parameters here. So then we zoom in the figure at 26 dBm power with different impedance here. So you can see that center, the number is here. We have 2 dB room. So then we move from 42 to 40 because 40 is the acceptable level. Then we can go further to lower the less current here because the original current is 350. Now we can go further to go down to 300, and then we can also have the good ACL minus 40. So that's why we move the impedance point that such that the current is minimum with acceptable linearity. Acceptable meet the 50 PV standard. So here, original from data is 50 ohm is here. Then because we want lower current with acceptable linearity, so that's why we also lead the matching level outside the palm so that we can move the point from here to here. The point means the impedance from here to here so that we can give the lower current with the acceptable linearity. So here is just the example how to do the matching. So the left side is the fully matched 50 ohm board here. And then the right side is the palm center is a chipset with input matching, output matching. And also this one is the duplexer. And then this part here is also the matching network. And then the RS part here, antenna part here, and then all the matching network, we use the pipe type lumped network here. So then you can see for the here, looking here, 50 ohm fully matched is the left side, this spot. So the power is at 26 dBm, the current 300, linearity is minus 40. So then when we go to the mobile phone, we deliver 22. So we change the value based on the contour provided by the palm supplier. So for example, you see here at the beginning, this one component 1 here, component 1 here, component 2 here, component 3. Then based on the datasheet or low pool contour provided by the supplier, I add the component here. Then I measure the 22 dBm power here. So that you can see the current here, but the ACL is bad. Then the second procedure is fine tune to optimize the performance because in the RF, there's the component variation, and then because we can't make the very precise circuit, precise tuning, that's why go to step 2, we need the not try and error, just step by step, for example, 1.8 to 2.4 to further optimize the performance. Then you can see that I do multiple type iteration. You can see that I can achieve the best performance at component 0.5 pico, 2.7 nano here. So then finally you can see that the current is here to 267, and the ACR also meet minus 40. So under 22 dBm. So then I can achieve the best performance here. So that's why in this present, I want to let all of you that when the amplifier is maybe we can know it's a microwave design, but the case is we buy from the fully matched palm, so we can buy from the market, and then we just use the chipset in the front-end circuit. But the case is we also need to do further design, further matching based on the load pool, such that we can optimize the DC consumption and also the reliability. And also we also consider the reliability and also this is also very high cost component in the front-end circuit. That's why Pi is very important in the mobile and IoT system. And then Pi modules dominate the mobile phone front-end circuit, especially it will affect the 3GPP standard because of the linearity issue. That's why for the future 6G and higher data rate modulation, there is more challenge in the wireless front-end circuit in mobile and IoT system. So that's the end of my presentation. Thank you.
Thank you, Steve. Thank you very much for your kind presentation. Really interesting. I wonder whether is anybody here for asking one question to Steve. I don't know, for example, Masato, Professor Masato, if you want to ask your question to Steve, since you are in the same technical committee and area.
Okay, actually, I'm on the same technical committee, but I don't know so much about hardware. It says, well, I want to know if the future, what's the future direction? Is it the same architecture for the higher data rate, or the architecture should be changed? What do you think about that?
So for the because now the topic is talk about GAN. I don't know whether you heard it before. GAN is now a hot topic. So maybe the future is the GAN merge to the move on. But the case now, GAN need the high voltage, and also the price is very expensive. So that's why the direction maybe we go to GAN, or also maybe the process will become better and better, so that it can give better reliability, so that we can reach more higher powers, give better efficiency. This is the trend in the market. So because the reliability is due to the device issue in the transistor. So that's why if the process is good, so the amplifier is also good. So of course there is many techniques for improving the reliability, but we can also apply this kind of technique.
Okay, thank you very much.
Thank you, Steve. Thank you, Masato. Is there any other questions from the audience? Okay, it looks there is no more questions to Steve. So it's once again me to thank Steve for his kind presentation and availability, and also to further thank Masato for the availability of his technical committee to hold this part of the technical talks. Thank you very much, much appreciated. So I switch to the second speaker of today, Dr. Lorenzo Vacchi. He is from the CSH Technical Committee, which is the technical committee I belong to. So Lorenzo is from Italy, from the National Research Council of Italy, Institute of Clinical Physiology in Pisa, and from the Scuola Superiore Sant'Anna of Pisa. His speech will be entitled Automatic Electrocardiogram Signal Processing and its Applications on Healthcare Devices. So I leave the floor to Lorenzo for his presentation. Please.
So thank you, Alessandro, and of course, thanks the technical committees for inviting me, and also thanks to Fabrizio Lamberti for organizing the event. So we'll proceed now to share my screen. So hope you can.
Yeah, you can go full screen. Perfect.
It should be on.
Go on. Thank you.
So thanks for inviting me again. And my presentation will be quite descriptive of everything that happens inside of many ECG recording devices. And of course, this presentation will be not quite on the specifics, but aims as to give a general idea and of some of the most established methods, which I think are very interesting, very fascinating in solving the quite deceptively difficult challenges in ECG processing. ECG processing may look quite easier than it actually is, especially on some devices. And we will get to that in a moment. So first, as Alessandro very kindly said, I'm a biomedical engineer, currently doing research work at the Institute of Clinical Physiology, National Cancer Research of Italy. I do my research work with Lucia Bilesi and Maurizio Varanini, and I have an active collaboration which has been going on for some years with an Italian company that manufactures ECG monitors called Cardioline. I am just wrapping up my PhD, which I did at the from Sant'Anna School of Advanced Studies in Pisa. Perhaps I can hide this. I don't know. Yeah, maybe I can go here. All right. So moving on. So the electrocardiogram, in general, what it is, it's the recording of the electrical activity of the heart. And we can consider a simplification of the heart as an electric dipole immersed in a conductive medium with low conductivity. Typically, the electrocardiogram is recorded by using at least 2 electrodes placed on the subject's skin. And then these 2 electrodes connected by wires are connected by wires to set of electrical circuits, mostly amplifiers, and very importantly, galvanic separation. We don't want to zap the subject with the network electrical current, common mode rejection, and of course, conversion from analog to digital signal. Then the signal is processed with a few steps that I will describe in a while. And then, of course, these results, as well as the recorded signal, are displayed. So very briefly, the heart is made of 2 upper chambers, as you know, the atria, and 2 lower chambers, the ventricles. The right half of the heart is tasked with pumping blood into the pulmonary circulation, while the left part of the heart is tasked with pumping blood into the systemic circulation. And the contraction of the heart is typically initiated in a sinus node. You can see it here, that where the action potential propagates to the myocardium, crosses the atrioventricular junction, and then further depolarizes the ventricles in this system of bundle of His, bundle branches, and then Purkinje fibers. And the path taken by the action potential on the cardiac muscle determines the pattern, the shape of the ECG signal. So this is typically the normal beat as it appears in lead 1 and 2. These are the 5 characteristic waves of ECG: a P wave, Q, R, S, T. The P wave relates to atrial depolarization. The QRS complex relates to ventricular depolarization, and the T wave relates to ventricular repolarization. Of course, the repolarization of the atria happens, but is shadowed by these much higher waves. And so if for some reason the action potential takes a different path on the myocardium, the heart muscle, the resulting beat will have a different shape. And this is very important because detection of cardiac abnormalities allows the assessment of the functional state of the heart. These abnormalities may be either a sign of disease or also a risk factor for some other disease. And this is quite a typical example. So under 1,000 ventricular beats, premature beats per day, of single shape, not coupled, it's perfectly fine, happens to most of us. However, frequent ventricular beats over 1,000, even more, with different shapes, often there can be 2 or even 3 different shapes, appearing in complex triplets. This is suggestive of heart disease, and clinical, let's say, assessment is warranted. Now, how is ECG measured in different devices? So a more standard way, most of you might have had one in their life, 12-lead ECG is recorded with 10 electrodes placed on the subject's skin. So 4 electrodes go on the limbs and 6 electrodes go on the torso. And these are called precordial leads. And these are the typical leads of the Einthoven triangle. So basically, from these 10 electrodes, we get 12 different leads or channels. So we see here a typical example of resting ECG. This is typically recorded in hospital with very controlled conditions. So it's usually, it looks very pretty as this one. Now, there are also other settings and other devices that are used to record ECG. Of course, stress ECG is recording during physical exercise on either a treadmill, shown here, or a bicycle, to observe the ECG changes due to increased heart activity, such as ischemia. And what we can see here is what happens when at rest we see no particular abnormality, but in exercise we see a sign of sufferance of the myocardium. And also a very famous setting of ECG recording is Holter ECG, where ECG is recorded for 1 day up to several days. Used mostly to detect rare events, monitoring drug effects, also assessing circadian variations, assessing symptoms reported by the subjects, which may feel palpitation or something like that, and also used to for risk stratification. Typically, 3 independent channels are recorded from 5 electrodes. And we see here why is Holter used. These are perhaps rare events then that when you go to the hospital to take a short ECG of 10 seconds, you might not you might not able to record. But during the course of 1 day, these very important events, this is a non-sustained ventricular tachycardia, are very relevant for the clinical, let's say, diagnosis, eventual diagnosis of the subject. Of course, there are also other devices that are used, especially for longer periods of time. The Holter monitor, let's say 1 week or 1 month, it's quite uncomfortable, cumbersome. So patch devices are used, and typically they have 2 different independent channels. However, the signal quality is generally lower. Of course, this is due to many things. For example, the very close proximity of the electrodes. So if something happens here, the other electrodes, of course, will record the same interference. And also portable devices have been proposed and are getting quite popular in the general public. We see 2 very also famous examples, the Cardia LifeCore and Withings smartwatch. Of course, these are not, strictly speaking, medical devices, so they must satisfy less regulatory requirements and can be used only for informative purposes. And yeah, so what is what happens in ECG signal processing? So oftentimes, especially in ambulatory settings, the raw signal, the one that comes from the ADC converter, is something that looks like this. So there is no flat baseline. There are very sources of noises reducing the signal quality. And what we want to get is a clean ECG. So first, we perform noise reduction. Then heartbeat detection. We want to know where heartbeats are, so we can calculate heart rate and so on. Sorry, I have a bit of a cough, so forgive me if I'm coughing along the way. And wave delineation is also very important to determine these measures on the ECG, which are relevant to the health status of the subject. Then beats are classified in normal ventricular beats, but they can also be paced beats from pacemakers, and there are, I mean, other groups are on T beats. This is beyond the scope of this presentation now. And of course, arrhythmia detection, one of the most important aspects of ECG recording. So I described briefly before different settings on where ECG is recorded. And of course, different settings require a different complexity in processing. Of course, the resting ECG, the hospital, as I said, is performed in very controlled conditions for short duration, so not much processing is required. Then, of course, as we change the setting, let's say portable devices which are worn on free living conditions require a modicum of signal processing, even to only detect heart rate. And most of these devices have the ability to alert for atrial fibrillation episodes. And of course, stress ECG, right? So the analysis of ischemia presence or the handling of muscle noise. And then we will go to that in a minute. And also the most complex analysis stages are required for Holter and especially patch devices, which they suffer from many sources of noise. So what are the noise sources in ECG? Baseline wonder, low frequency oscillation of the signal's baseline, electrode motion artifacts. They can manifest in a broad spectrum. They don't have like a set frequency bandwidth. Muscle noise, which results from the activation of skeletal muscle and has an overlapping frequency content with ECG under 100 Hertz. This is quite problematic. And of course, also respiration affects the amplitude of the ECG due to the changes in heart position and lung conductivity during the respiratory cycle. Now, we can see an example of what these four different sources of noise. Baseline wonder is reported here. Electrode motion, as you can see, these are spikes that can also be mistaken for heartbeats. Muscle noise, we can see here a typical EMG signal, and the modulation by respiration. And then, of course, another common source of noise in ECG is power line interference caused by electromagnetic coupling between other devices and the ECG monitor. And this happens for many other medical and non-medical devices as well. So, getting back to baseline wonder, so there's low oscillation that can be removed with a linear phase low-pass filter, typically with a cutoff frequency of 0.67 Hertz. A finite impulse-to-response filter can be used, but usually it takes quite a long, high order, or also forward and backward infinite impulsive response filters. They're more complex, but they also afford a lower filter order. And the cutoff frequency of the EIR filters can also be made time varying, depending on the current heart rate. So basically, this cutoff frequency can be moved up from 0.67 Hertz to perhaps 1 Hertz. And you can see here that by making this cutoff frequency time varying, depending on the current heart rate, the original baseline wonder is further reduced. This is without time varying dependency of this filter, and this is with time varying dependency of this filter. Now, another popular method of baseline wonder removal is a subtraction of a polynomial estimate of the baseline. And as you can see here, they are the beginning of each course complex is detected. And then, so we basically a set of points is collected. And then this set of points, okay, placed here, 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 are then interpolated by a polynomial. And then this polynomial is subtracted, ending in a signal just like this. Now, about power line interference, the interference from the network frequency at either 50 or 60 Hertz can be removed by notch filtering although the narrower the stop band, with narrow stop band, ringing artifacts are introduced in the signals due to long impulse responses. Now, these artifacts are unwanted because they introduce ringing even in clean signals. So we want this, and this can be achieved by using a different method, which is not a notch filter, but subtraction of a sinusoid, a network frequency, where amplitude and phase are estimated from the signal. So we have our own sinusoid, and then we estimate its amplitude depending on the error here in E between the actual sinusoid we see on some segment of the signal, which is devoid of cardiac activity, and our own signal and our own sinusoid. And this estimation of the sinusoid depends on a coefficient. Of course, the higher the coefficient, the faster the filter will be. But also this may also imply that without even a network frequency, this could still, let's say, introduce unwarranted noise. So it must be, of course, a compromise. Now to muscle noise. So as I said earlier, the overlapping frequency content between ECG and MEG signals the reduction of muscle noise is challenging. However, when multiple channels are available, redundancy can be used to reduce uncorrelated noise. So what can be done is a transformation between channels by either least squares regression or with singular value decomposition, of course, only between independent channels. Then each channel is reconstructed by a prediction using all other channels. We see here on the right 4 different filtering methods in, of course, extreme conditions of muscle noise. And of course, if we cut off the signal with 25 Hertz low pass filter, we end up cutting off a bit of ECG. Using a 40 Hertz low pass filter, we end up, not cutting as much ECG but also we, let's say, remove less noise. So these other methods allow to not affect the ECG, especially QRS complex, while also rejecting a portion of muscle noise. And noise presence can also occasionally hide the proper ECG signals on all available leads. And when, let's say, this noise episode or these noise episodes are detected, they should not be analyzed because they could be mistaken for arrhythmias and called false alarms. So this is a clean ECG. This is noise, and we want to avoid analysis of this noise episode. But this, instead, is not noise. This is a ventricular tachycardia. So the noise detection aspect in ECG processing, especially for Holter and patch devices, is challenging. How is it done? Noise detection is traditionally performed by using noise indexes, such as kurtosis or relative power in the QRS complex. These noise indexes are then used as features of a classification model or a decision logic as well. And then, of course, signals, let's say windows of signal labeled as noise are discarded and do not participate in further analysis. So everything that is not discarded as noise after noise reduction, so we reduce the noise we can reduce, and then we discard the noise that we cannot reduce. Heartbeat detection is performed, and it is a fundamental step of ECG analysis. Generally, each detection algorithm is articulated in 3 steps. Further noise reduction, especially to reduce the influence of QRS-like artifacts. QRS enhancing to avoid detection of other waves, such as the T wave, and decision logic with sets of adaptive thresholds, just like the one seen here. After a successful detection, the threshold is switched off, and then it decreases linearly with time. Many QRS detectors available today are based on the original approach of Pan and Tompkins, where the ECG is first bandpass filtered, then it is derived, squared, and possibly, yeah, moving averaged. So we turn this original signal here in a set of very recognizable spikes, which can be detected with threshold. Of course, QRS detection is complicated by notable heterogeneity shown by ECG signals in different leads, and especially for different abnormal conditions, which are more difficult to detect, but are the ones that you really want to detect. The doctor really wants to see those. So no detector proposed so far has proven to be perfect, and at least for now, one day perhaps artificial intelligence will be able to surpass the human capabilities. So it will, every detector will have some false negatives and some false positives. Then lastly, the last aspect I want to highlight, because I think the time is running. Another key aspect of ECG analysis is the accurate computation of clinically relevant parameters, which include the PQ interval, the distance between the P wave and the Q wave, associated with atrioventricular block and generally the function of the atrioventricular junction. The length of the QRS complex, which means the distance between the beginning of the Q wave and the ending of the S wave. Fundamental parameter in the classification of ventricular beats, as well as a major index of ventricular conductivity. Lastly, the QET interval, which is a marker of ventricular repolarization, arrhythmic risk, as well as sudden cardiac death due to long Q3 syndrome and other things. So very briefly, this is just two ways that, or at least I should say, two different methods for calculating the T end and the beginning and the ending of the QRS complex, as you see here, that are based on mostly derivative of the signal, because the ECG is mostly characterized in time and not as much in the frequency domain. So we work in the time domain using derivatives. For example, for detecting the beginning and the ending of the QRS complex, the algorithm starts from the maximum slope before the Q wave, which has been previously detected by some algorithm. Then we go back until the slope or the derivative falls under a certain threshold. The same mirrored happens for the QRS offset, the ending of the QRS complex. As for the T end, the ending of the T wave, we compute the baseline line, and this is one of the reasons why accurate baseline wonder reduction is important. And then we take the intersection point with a tangent to the maximum slope of the T wave. So in this presentation, I have briefly covered the, let's say, first four stages of ECG processing. Of course, there's more, but I think the most interesting signal processing methods have been, of which I gave a brief overview, have been devoted to these first four steps. And I think this is it, and I hope you enjoyed this presentation.
Thank you, Lorenzo. Thank you very much for your inspiring presentation. It's a little bit of a lectio magistralis in terms of the ECG signal processing, and really appreciate it. So is there any question from the audience? Yeah, please, Professor Elena Bertozzi, you can ask, please.
Hello, thank you so much for a very interesting presentation. I just had a question because I've been working with some people who are working on smart fabrics. Like, I'm wondering if there are, for example, very tightly fitting underwear, for example, that could collect heartbeat data from like around wrists and ankles and around the chest that don't involve electrodes that are stuck on the skin. I'm just curious if there's been any advancement in smart clothing or other smart fabrics that are able to collect heartbeat data accurately.
Well, indeed, there are, let's say, many approaches to smart fabrics being developed right now. I think there's also like a startup in Pisa dealing with smart fabrics used for let's say, record some biomedical signals, including ECG. I think that it's still a technology that is being developed right now, because the problem is the signal quality. Because of course, if you want something that is not an electrode attached to the skin, the contact will not be perfect. And so what you can see, you can definitely detect a heartbeat. But the thing is that you could detect a heartbeat even with like a small bracelet. So the advantage for now, at least as I understand it, is quite limited. But I think that with new technology, for example, tattoos, electrodes, things might indeed take off. Thank you for your question.
Thank you.
Thank you. Other questions from the audience? Okay, so I have a very short question. Indeed, we are running out of time. I would like to ask to Lorenzo, since I know his contribution to the state of the art is really significant in this specific domain. Which are, in just 30 seconds, more or less, which are your main contributions to the state of the art?
Okay, so 30 seconds starts now. So basically, I have worked on several stages in CG processing. A few pictures of the presentation were taken from some of the works I have been an author of. So curious detection, we worked on quite fast curious detection algorithm which is suited for, let's say, portable devices with low battery, so they must be quite efficient. And also noise detection, which I really skipped over it, but it is quite still unsolved issue, especially in the presence of arrhythmias. Lastly, the simulation of ECG, which is actually useful for developing new methods of ECG, because there's not a lot of data available which is annotated due to privacy reasons and all of that. So just 3 things, and I think I've run out of time.
Thank you, Lorenzo. You are on time. Really kind effort. So I see from the audience that somebody asked about the possibility to have a copy of the presentation. If there is no, no matters from Lorenzo and from Steve, I would like to, to share without problems. So please refer to Professor Lamberti, maybe send him an email with this kind of request, and Lorenzo and Steve, I think they are pretty happy to share their presentation with you. Right.
All right.
Okay. So thank you, everybody. There is still one message. Sorry. Okay. Thank you, everybody, for your participation of today's technical talk. So the next talk will be roughly in the month of June. So have a nice day, and see you next June for the 9th session of the technical talks. Thank you, everybody, and
Thank
goodbye.
you.
Bye bye.
Thank you.